Hi, everyone. This is the video for number 3 for the Physics 121 summer class in the year 2020. Today, in this video section, we're going to talk about Cartesian unit vectors. So, Cartesian unit vectors. So what's our plan here? What are we going to try to do, and how are we going to try to do it? The idea is we're going to take the language of vectors, which we've talked about in the video clip that was put together before this one. And in that, we reminded you of the vector of mathematics that you ideally absorbed when you were in high school. The idea that vectors are things that have if I have a vector, so there's my vector, and I'll label it A, and I'll put a little arrow on top of it to make it clear that I mean a vector. And when I do that, the vector is got a length and it has a direction, which correspond to some quantities that I can measure. So the length corresponds to how long this is, and the direction I have to pick a heading. So that the usual trick is to measure the direction relative to the horizontal, which we're going to call the x component. So I'll call this angle theta. And so I've got a length A and a direction theta. Those two numbers represent the vector. But of course, I have this alternate scheme, which we've talked about a couple of times now, where instead of representing the vector as a length and an angle, I can represent the vector in terms of two components. And I'll call this component, the horizontal component, A sub x. That's got a vector on it. So that's a vector, A sub x. And then this vertical component is the vector A sub y. And once I've done that, I can write down, excuse me, I can write down the vector equation, which is that A is equal to the vector A sub x plus A sub y. So this is just a review of what we've already talked about here. And the key idea of this equation, the thing that I really want to point out, is that the things on the left and the right are both vectors. They're not numbers. And the technique for making the case that this is a vector addition is this graphical technique where we go tail to head, and then the two together give tail to head. So we have a mechanism for doing vector algebra. Well, not really algebra, more like vector geometry by basically doing a graphical representation. So this is the concept that I've got here, and this is the concept of what we'll call vector addition. And I want to kind of add another concept, which again is something that we ideally all learned in high school, and that's basically vector multiplication by a scalar. So when I use the word scalar, that is a number. It's just a single number, whereas a vector is something that has both direction and magnitude. It corresponds to two numbers. The idea is pretty straightforward. I could basically talk about a vector C, which is equal to some number. So I'm going to label this little a that represents the scalar, and I'm going to multiply it by some other vector B. So what do we mean by this multiplication, and how does it work? So if I have a vector, so I'm going to call a vector like this vector here, I'm going to call that vector B, and B will have some length. And then a vector C is A times B. Well, the definition basically says that the vector C is just the same vector as B, but now with a different length. In other words, C basically points in the same direction as B, and the rule is simply that the magnitude, the length, so remember when I write down absolute value C, that's the same thing as C. That means the length of the vector C. That's going to be equal to the magnitude of A times B, which is simply going to be equal to, since this is just a multiplication, that's just going to be equal to A times the magnitude of B. So in other words, it's just going to be AB. So in other words, C, this magnitude of C is just A times the magnitude of B. So the way to think of this multiplication is very, very simple. That C, that if I take a scalar and I multiply it by B, I get a new vector if I take a scalar and multiply the scalar times a vector, I get a new vector whose magnitude is just equal to the magnitude of these two things together. That's not so bad. So we have vector addition, and now the multiplication of a vector by a scalar. Oops. So what? All right, so let's look at let's suppose, just in case in a particular case, suppose that the magnitude of b has a special value. A special value. What will that special value be? We'll call it 1. So in other words, I can define a vector whose magnitude is equal to 1. 1 what? Well, 1 whatever unit you happen to be working in vector space out. If you're doing vectors of, say, velocity, it'll be 1 meter per second. If you're doing vectors in force, it'll be 1 newton. Whatever your favorite thing is, but it's basically just 1, right? So this thing is called a unit vector, where the word unit is mathematical for unity, which is to say 1. And so if that's really true, then if I say define a vector c, which is just equal to a times b, a times, sorry, that's up. Let's try that again. A vector a times b, then that vector, then it must be true so that the magnitude of c, which is just equal to the magnitude of a times b, that's just going to be equal, because the magnitude of b is 1, that's just going to be a. So in other words, if I take a and multiply it by a unit vector, I get a new vector whose magnitude is just c. In other words, every time you take a unit vector, and multiply it by a number, you get a new vector whose length is just equal to that number. Okay, well, that's cool. So what? So suppose I define a new vector. So this is a new vector here. I'm going to define it, and I'm going to define it for all time. I'm going to define a vector called I with a caret on it, I hat. Now, you may have seen this before, but I'm not assuming that you have. I'm assuming this is actually a new thing. It's usually introduced in the calculus text instead of a physics text, but that's okay. Sometimes people call it x hat, but I'm going to just call it I hat so that we don't mix up the unit vectors with the coordinates. And I hat has the following properties. The magnitude of I hat is equal to 1. It is a unit vector. That's the thing. And then it basically, I hat points in the x direction. So in other words, whatever way x is in my coordinate system, so if that's x and that's y, then I hat points the same direction as x. And it has a unit magnitude. So this is important. I hat is a vector. This is very important. Even though I put a caret on top of it instead of, I call that a hat, right? It's like a little hat. So even though I put a little caret on it, what this thing is a vector. It's not, I hat is not a number. If I say, what is the value of I hat? That's not a sensible thing. I can say, what is I hat? I can say, I hat is a vector whose direction is in the x direction and whose magnitude is 1. That's its magnitude. If not, it doesn't have a value of 1 because this is not the number 1. This is a vector. It's not a number. Okay. And likewise, I could define another vector that points this way in the y direction. And again, the magnitude of, I'll call that j hat, and the magnitude of j hat is again equal to 1. So these things I hat and j hat that I've defined, they're called Cartesian, which is because they're pointed in the x and y directions. Yes, x and y. They're called Cartesian unit vectors. Okay? And so what? Well, what good are they? Well, the reason they're good and the reason we love them in introductory mechanics, especially kinematics, is because they give us a mechanism for doing algebra with vectors instead of having to deal with everything graphically, like on a piece of graph paper or with tail to head, this kind of thing. So how does that actually work? So suppose I have a vector. So again, I'll take my favorite vector here, which is A, and I'm just going to reproduce what I've done before, which is to say I'm going to have break it into components. So this is A sub x, and this is A sub y. So we've already written this equation 10 times. A is equal to A sub x plus A sub y. So that's a vector equation. That is a vector equation. See what I'm saying? This thing here is, this vector is equal to the sum of those two vectors. But if I have the coordinate system like this, if I've got a coordinate system where that basically points in the y direction and that points in the x direction, then by definition, I have these two little unit vectors. Here's one here, I hat, and here's another one here, j hat. J hat points up, and I hat points to the right. Okay? So in other words, j hat, I hat points this way, and j hat points this way. And the key issue is that these things, you can pick them up and you can move them, but the point is that they're aligned with the x component of A and the y component of A. So for example, I can write A sub x, the vector A sub x, is equal to its magnitude, right? A sub x. So in other words, when I write this thing, this is a vector, this is a magnitude, times I hat. Scalar times a vector is equal to a vector. This thing, A sub x times I hat, is equal to this thing, A sub x, because they both have the same direction and the same magnitude. And likewise, I can write A sub y, the vector, A sub y, is equal to the magnitude, A sub y, times j hat. Okay? Again, these are vector equations. The two things that we're talking about here are, on the left and the right, are vectors. The A sub x, this is a number, this is a number, that's a vector, that's a vector, that's a vector, that's a vector. So what? What good is this? Well, what good this is that once I've done this, instead of, if I want to do vector addition, if I can take a vector and break it into components, A sub x and X sub y, whose magnitudes I can calculate, which you've already seen, then I can do algebra on those magnitudes instead of having to do the geometry on a piece of graph paper. So for example, suppose I have two vectors, which I've broken into components. So I'll say A, well, A can be written as A sub x times I hat plus A sub y times j hat, just the way I've basically done here. This A is equal to this plus this, so that's equal to this plus this, which is just equal to this plus this. So A sub x times I hat, okay, this is what I call a vector, Cartesian unit vector representation of A. I've taken A, I've broken it into its component, I've figured out the magnitudes of the two components, and then I multiply the x component times I hat and the y component times j hat. And then likewise, I could have B equal to B sub x times I hat plus B sub y times j hat. Okay, I'm just going to erase this here because I need the room. And then I could do some algebra, right? If I say, okay, let's calculate what the vector A plus B looks like. Well, that's just the sum of these things. So I say that's equal to A sub x times I hat plus A sub y times j hat plus B sub x times I hat plus B sub y times j hat. No, they just wrote down that the sum of these two things is the sum of these two things. That's easy. How do I deal with this expression if I want to simplify it? Well, I combine like terms because these are two vectors that are pointing in the same direction. So if I have two vectors that point in the same direction, one on top of the other, but the magnitudes, they've got the, you know, if I go 2 this way and 3 that way, that's 5 that way. So whatever these two things are that are in the I hat direction, they add. And likewise, the things that are in j hats. So in other words, the I hats and the j hats can be thought of as apples and oranges, or, you know, these things and those things. You can collect like terms, right? In terms in the language of algebra. So in other words, this is just equal to A sub x plus B sub x times I hat plus, again, A sub y plus B sub y, all collected, times j hat. So in other words, I have a way of determining, of course, this thing here, that is the x component of this some vector, right? So, if I've got a and b, this is the x component, its magnitude, because it's whatever goes in front of I hat, that's the x component, and this is the y component, right? So, for example, if I defined a plus b is equal to c, then this thing here would be c sub x, and this thing here would be c sub y. So the technique of taking vectors, breaking them into components, and then writing them in this notation, which again, we call this notation here, just to make it clear what I mean, this is known as vector Cartesian unit notation. And sometimes I will move the words around. Sometimes I'll call it Cartesian unit vector notation, and sometimes I'll just call it vector notation. The technique is to basically rewrite the vectors in terms of the I hats and j hats. And that gives you everything you need to represent these vectors in 2 dimensions. By the way, we're not going to do it now, but later on in the semester, when we go from 2 dimensions to 3 dimensions, coming out of the board, towards your head there, that vector there points in the z direction. There'll be a Cartesian unit vector for z hat, for z. If I hat is for x and j hat is for y, then z will have k hat, right? So in other words, I can just extend this notion of writing a vector into x and y components to writing a vector in terms of x and y and z components. But we'll get to that later. That's all for now.